Okay, problem 424 says the velocity of air in the diverging pipe shown in the figure is given by the velocity at location 1 is equal to 4 times t feet per second, and the velocity v2 is equal to 2t feet per second, where t is in seconds. It says A, determine the local acceleration at points 1 and points 2, and B is the average convective acceleration between these 2 points 0, negative, or positive, and try to explain. Okay, so we'll start off with part A. And part A just says, what is the local acceleration? Okay, so we must remember that the acceleration in our Eulerian description, we need to think about the material or substantial derivative that says the acceleration, right, is equal to the change of velocity with respect to time, and that's equal to the change of velocity with respect to time plus u change of velocity with respect to x plus v change of velocity with respect to y plus w change of velocity with respect to z. Okay, this is the local acceleration, and these last three terms are the convective acceleration. So simply part A, to find our local acceleration, at point 1, that's just equal to the derivative of u, because our v1, right, is only in the x direction, so that's equal to u. Okay, and v2 I could also say is equal to u2 because it too is purely in the x direction. So I'll have my local acceleration is the change of u with respect to time at location 1, and that is a simple derivative for t with respect is just the derivative for t with respect to t is just the constant 4, right? And the derivative at location 2 is just the derivative with respect to t of this one I'll write out, 2t, and that's just equal to 2. Okay, so these are our local accelerations, 4 and 2. And now it asks us part B. It says, tell me if the average convective acceleration is 0, positive, or negative. Okay, so because we only have velocities in the u direction, this guy goes away, this guy goes away. So my convective acceleration, I'm going to focus on this. It's going to be u, right, the partial, looking at the u direction, u dx. Okay, so that is the expression for my convective acceleration. So I'll note that u, I'm going to define it, right, that it's positive in this direction, and therefore u is always positive. Okay, so that's positive. Now let's take a look purely at the derivative du dx for any time t, right? So that's going to be approximately the change in u over the change in x. I can say, make up some value for this change in x. I can call this L. Okay. So my change in u is at point 2, the velocity is 2t minus the velocity at position 1 minus 4t over delta x, which is L. So that's going to equal a minus 2t over L. So now you see that that derivative partial u with respect to x is always going to have this negative sign, okay? And since this u is positive, I can say that the convective is always negative. Okay? And we did that by proving that this derivative here must always be negative.